All right, so yeah, this is just a quick review of what we mean by radians, what we mean by rotational kinematics, and how we might locate an object that is going around in a circular path. Okay. And you may be wondering, well, what does that have to do with harmonic motion? Well, we're going to come back to that. So, come on, move out of the way. There you go. I have too many windows open, tracking chat, participants, layers of my drawing. I really could use a second monitor. I'm going to put that on my wish list for Santa. Okay.
For that exact reason that I made sure to have 3 monitors so that I could have enough screen space to be able to keep track of everything.
Yep. in my old office, back when we had offices that weren't our homes, I had a 3-monitor setup so that I could program on one monitor, have reference materials on one monitor, and have YouTube on a 3rd monitor. But yeah, my home office is not nearly as nice as my office was. Yet. I like your optimism. So you may remember from Gen Phys 1 that we had Hooke's law, which described how springs reacted under deformation. So if we have a spring, and it would normally like to be yay long, and instead we pull it out of position so that it's got this extra bit. The force that spring will exert in trying to right itself is proportional to how far we stretched it, and it will be the opposite direction that we stretched it in. So if we stretch it down, the spring is going to pull up. So that negative sign is just an indication of direction. And also, not all springs are the same stiffness, so we toss in this material parameter K. Okay. Now this is an algebra level only class, so we're not going to go into how this is derived, but you will have to take it, take my word for it, unless you would like to talk about differential equations. But when we have an equation of this form, where the force is linearly proportional to the change to the displacement of position, the solution for the position as a function of time. So if you stretch it, you let it go, it's going to wobble up and down. The solution for this as a function of time is going to be some sum of sines and cosines. So in our treatments here and in the book's treatment, we normally say that this b is actually 0. Since we want it at time 0, we want the position of the spring to be all the way stretched, and we want the velocity of the spring to be 0.
Okay, I have a question.
Yeah.
For the k over m on both sides, does the square root cover just the k or the k over m as a whole?
That's a great question. It covers the k and the m.
Okay, thank you.
So maybe I should write that instead as k over m to the 1/2 power. And then this A here is just the amplitude. That's how far we stretched it. All right.
Really quick, with the equation that you just wrote, so it's k over m and then the exponent's 1 over 2?
Mm-hmm.
Okay, perfect. Thank you.
Yes. Where to the 1/2 power means square root.
Gotcha.
So that actually, combined with our first page, okay, we made the note that the x component of a particle going around a circle that's really similar to our consideration for how an oscillating spring would behave. And so we actually end up co-opting the language of polar coordinates to describe oscillation. Right? So we make this connection that actually the square root of k over m is equal to omega. So omega is maybe a little bit of it's a little bit opaque. Like what does omega actually mean in a physical sense? Let's draw a graph. This will give us a chance to talk about just how waves work in general. So we'll put t, so time will be on the x-axis, and on the y-axis will be our x of t. Right. I'm going to sketch out a cosine graph here for us. Actually, let's make it a little more compact than that. You could all freehand sketch a cosine graph if you had to, right? Okay. Pretend this was an expertly done cosine graph. The distance between peaks, right, on this this displacement versus time graph. So the distance between peaks, we call that the period of the wave. So how many seconds per one cycle of the wave? So that is the thing that is most easily observable in a physical sense. However, because a lot of the waves that we are going to be dealing with, sound and light and whatnot, they're actually really short, like really short amounts of time between peaks. So frequently we're going to talk about the reciprocal of that. Instead of thinking about how many seconds per one cycle, we're going to think about the frequency. which is how many cycles per second. And the SI unit for this is hertz. And this frequency is related to our omega that we went through up here. Right? So omega is how quickly we're going through going around a circle, where frequency is how quickly we're going through a cycle. But if we equate those, right? If there's 2 pi radians in one cycle, then 2 pi times our frequency is going to give us our omega here. So this gives us like a 3-way connection between the stiffness of a spring, the mass on the end of a spring, the angular speed or angular frequency of the spring, and the observable frequency of the spring. This is important to remember.
I'm sorry, could you repeat that one more time? I was just trying to connect between the angular velocity and the 2 pi frequency. How did you come up with the 2 pi frequency?
Yeah, so frequency measures how many cycles per second, right? So there's a little bit of unit conversion going on here. So if we have cycles per second and we want to convert to radians, then we can note that there are 2 pi radians in one cycle. Cycles cancels off. And that tells us that there's actually 2 pi f radians per second is our angular frequency.
Okay, that makes a lot more sense. Thank you.
Yeah, you're welcome. There is another way to sketch this graph, though, which will be important later. But since we're talking about waves, I want to cover it now. If instead of time on the x-axis, we were looking at, say, a direction. So if we're putting time on the x-axis and displacement on the y-axis, basically that means that this is a graph of watching one particular point and seeing how it behaves. So that would be like watching just the point on the end of this spring, watching how it moves. When we can do that, so yeah, that's one way of looking at it. If we are looking at water waves, which we are all familiar with, I think hopefully we've all at least seen the ocean in our lives. So you know that if you're looking at you can look at one particular spot on the water, and you can watch that one particular spot bob up and down. Or you can take a picture, like with your phone, and you can look at the entire surface of the water. And there's also going to be a regular spacing between wave peaks. In that case, the spacing between peaks at a particular moment in time, that we call the wave length. There is just like there's a conversion from period to frequency to angular frequency on the time scale, there's also a quantity related to wavelength that we call wave number. And it's 2 pi divided by the wavelength. All right. I'm running out of room on this slide, so I'm going to make some space.
K,
Sorry.
the K there is different than the spring constant, right?
Yes. It is one of those unfortunate events where we have just run out of English letters.
Just don't want to be confused about that.
Yeah. These actually came from two different fields. So the K for the spring constant, that comes from mechanics, and you had one set of physicists working on that, where the K from the wave number actually comes from people working with X-ray radiation. And they didn't really talk to each other when they decided to use K as a as a variable in both disciplines. But now they are smushed together because we recognize that light is in fact just waves. So we're stuck in this case where K has two different meanings. It's unfortunate, but here we are.
I love it when that happens.
Wait till we get to it in a couple of chapters. The direction that current is defined around a circuit was defined before we knew it was actually electrons that were doing the moving. So the direction of current in a circuit is opposite to the direction of electron movement in a circuit. That's going to drive you crazy in a couple of weeks. So this is nothing in comparison. Oh, there's a baby.
Sorry, I've got 3 kids and my wife's arm is hurting her.
No, I get you. I got 2 of my own. So
Yeah, she just woke up and she wants to learn.
all right. Let's take a break from listening to me talk. I have a video I would like to show you all.
Sir, what was K called again? Nicholas was asking in the chat.
Oh, wave number. And all of these are this is all going to be on YouTube by Sunday, if you want to refer back to it later. So this is all a little dry, which I recognize. Let's instead have a watch. Oh, this one's actually pretty cool. We'll come back to that one in a moment. Well, my WebEx crashed when I tried to share YouTube. So let's try that again.
Ahoy!
If anything, you can just send the link. We can watch it.
Yep, if it happens again, I will definitely do that. Okay, it looks like I'm going to have to send the link. This WebEx crashed hard. So I'm going to drop it in the chat.
Yeah, go for it. Whoa!
Now you may have seen a Rubens tube before. That's basically a pipe with a bunch of holes in it, and you pump in a flammable gas and light it on fire. So you basically create a row of Bunsen burners. What's really cool is to play some sounds into the tube, and you can actually set up standing waves. That is, there are areas, there are patterns of the vibration of the air where there's a lot of vibration in some parts and not very much vibration in other parts. Now that affects the flow rate of the gas inside that tube into the atmosphere, and so it affects the height of those flames. So basically you can visualize the standing wave pattern. I'm currently in Denmark with a team of physics and chemistry demonstrators who have taken this experiment to the next level. They've actually created a two-dimensional Rubens tube, a whole plane of Bunsen burners effectively. How many holes in this tube?
2,500.
2,500 in this pyro board.
Yeah.
So we're gonna see 2,500 little flames.
Yeah.
So do you want to light it up?
Yes, I really want to light it up.
Why did you make this?
Because we really like the Rubens tube, but then we thought, when you put on more fire, then it always gets better. And let's just turn it down. And then we can just try to find a standing wave. So this is below the lowest standing wave.
Ooh.
It's here. So it's really difficult to see it. We need a volume a little bit.
So what are we seeing here?
It's pretty much like the standing wave on the Rubens tube. It's just in this direction, and it's the lowest, it's the lowest frequency that makes a standing wave in this box.
So this is like the fundamental.
It's the fundamental.
Can you show me what happens when you vary the volume a little bit? Whoa. That was awesome. Okay, should we try to find another standing wave?
Yes. I think it's here. You can hear it before you can see it.
Whoa. It's weird. With the microphones, I can actually hear. Like here, I'm in a node. And then here, I'm in an antinode. Here, I'm in a node.
Because you can measure the sound pressure.
I can hear it. Like here is very much antinode.
I never thought about that.
This is a node, and you guys can hear it.
Yeah, that's true.
It's incredible.
Wow.
The flames
Yeah.
must be coming out in the antinodes.
The flames are coming up in the antinodes, yeah.
And you can even hear it.
Yeah.
That's
Nice that
incredible.
you can do that. Yeah.
That is awesome.
We just learned something.
Now what happens if we try to go higher frequency?
Here, we have something. Oh, that's a good one.
That is crazy. We're right in the antinode.
It's your ears, okay?
Oh god.
My ears are hurting now.
That was painful. Why don't we try to put something more pleasing to the ear through the speaker and see what happens?
I think that's a good idea.
Yeah, let's put some music on there. You ready?
Go.
All right, so that's one of my favorite demonstrations, because everything is better with fire, and you can see very clearly the pattern of wavelengths, at least in the one-dimensional tube, where you could see the peak, where the height of the fire actually corresponds to the pressure wave going through the combustible liquid or combustible gas at the bottom. So let's get toward understanding that from a physics point of view. Now again, I'm not going to cover every section of the chapters, so I'm not going to specifically cover, say, the pendulum, the simple pendulum, the energy of the oscillator, uniform circular motion, because I've already hinted at all of them, and also they are mostly straight reviews from Gen Physics 1. So what I would like to talk about then is what's section 16.10 in the book, superposition and interference. So the really interesting things start to happen when you have more than one wave happening at the same time. So if, for example, let's say we've got some tube. Pretend this is a pool, like an actual swimming pool. If you've got, say, some device, some plate that makes waves. This is how wave machines work, right? You've got some plate at this end that vibrates back and forth. So what you get is you get some pattern of waves. If you had another one of these devices on the other end, right? So it was also vibrating back and forth. Then you might have, another wave passing through the pool. Under most conditions, these just aren't, like the combination of two waves just isn't going to be that interesting, right? You add these together. Anytime you add two waves together, you just add the amplitudes from each wave. So if we have wave 1 plus the second wave, like we just add them up. So the resultant wave is just going to be and under most conditions, that's not going to be too interesting. There's a couple of pictures in the OpenStax book you should take a look at. There is one really interesting case, though. The interesting case comes from when we have omega 1 same as omega 2. So we have two waves with the same frequency. In that case, if we say that two waves are in phase if they are hitting their peaks at the same time. And we say they are out of phase if one wave is hitting its peak and the second wave is hitting its trough. So this high point up here is called a peak. This low point down here is a trough. And if we are matching peak to peak, we call this constructive interference. And if we are matching peak to trough, then we get destructive interference. For constructive interference, what we end up with is a wave that's just whose amplitude is the sum of the amplitudes of the two waves. So we can put two smaller waves into the pool and end up with a wave that's huge. Right? So the displacement is going to be sum of the two amplitudes. And if they are destructive, right, then we end up taking the difference. In the extreme case, where the amplitudes are actually the same, we just get flat water, even though we're pumping a lot of energy into it to try to make waves.
I have a question. I'm not sure if you have an answer to it though. So like with noise canceling headsets, right? Would they use a destructive like wave interference because don't they send like the opposite wavelength back through and like cancel out the sound waves?
That is exactly how they work. Yeah, if you have expensive active noise canceling headphones, then there is a microphone on the outside of those headphones picking up the loudest noises in your environment, and then it's got a speaker on the inside which is playing the same frequency but out of phase so that it cancels. So that the net thing you hear is nothing.
I have a question about that.
Yeah.
Wouldn't that, like, say you're listening to music, wouldn't that also cancel out the frequencies or the wavelengths of the music that are the same length?
Yes, it would.
So it also destroys music quality.
If you are a super audiophile, then yeah. You wouldn't want to listen to them on audio canceling headphones. In the extreme case, this means that if you, we'll get to that in a moment. But before we talk more about constructive and destructive, and we definitely will, I want to talk about one more property of waves that we haven't mentioned yet. So waves have a wavelength. That is, there's a spatial distance between peaks in a wave. They have a period, which is a time distance between peaks at the same point. And because they have a period, they also have a frequency. But the other thing that waves have is a speed. So the speed with which a wave appears to move, right? So if we're just sitting on the shore watching the ocean, we're seeing these waves, and the waves appear to be moving to the right. Let's say. maybe to the left, maybe away from us, maybe toward us. Depends on our perspective. But the wave appears to be moving. Now, when you're watching the ocean, the individual molecules of water in the ocean are not moving, right? This is so if we have individual atoms, they're vibrating up and down, but they are not actually moving side to side. Right? So in this case, the movement of the individual constituents of the wave are moving perpendicular to the direction that the wave itself appears to be moving. And there's a really good animation on Wikipedia. So actually, let's take a look at that. You may encounter instructors who hate Wikipedia, but that's because they're dumb. Wikipedia is maybe the most beautiful thing that humanity has ever come together to build.
I'm sorry, I had to step away for a second. What about Wikipedia?
It's the most beautiful thing that humanity's ever made.
Okay, but what led up to that?
Oh, we're going to look at an animation on Wikipedia about waves.
Okay.
So let me stop sharing my sketchbook for a moment. All right.
See if it'll work this time.
Is everyone seeing my Chrome tab? Yes? No? Maybe?
Yes, I do.
It's showing up.
Cool. Let's see if we can zoom in on this a little bit. Nope, it will not let it. Oh, there we go. So imagine each of the intersections of the lines on this illustration is like one molecule of water. And they can move up and down, but the actual molecules aren't moving to the right, even though the wave itself is moving to the right. This is what we call a transverse wave. So the actual constituents of the wave are moving perpendicular to the direction the wave itself appears to move. Water waves are transverse waves. So are light. We're going to get to that more later in the semester. But in light, the thing that is doing the waving is the electric and magnetic fields that compose each photon of light. So electric and magnetic fields are moving in, say, in this graph in the z and the x direction, but the photon itself is moving in the y direction. So that I'm sorry, go ahead.
Since the molecules aren't what's moving in the water as they're moving up and down, it's the energy in the water that we say. I'm standing in water and there are waves. It's not necessarily the elements that are moving up and down going in one direction. It's the energy that they have in moving through them that I feel.
That's exactly correct. So waves are at least the waves that we're going to be talking about, are a way of moving energy through a medium, energy and momentum through a medium without moving the medium itself on average. So this is now an illustration of a longitudinal wave. So the particles are actually vibrating back and forth in the same direction that the wave appears to be moving. Note that they're still not moving on average. So after the wave has passed it by, they return to their original positions, but there's still definitely a movement of the wave from left to right. So this is longitudinal. Sound waves are longitudinal. So when we have a sound wave passing through air, what we have is actually changes in the local pressure of the air. So the overall pressure of the air, right, in our home offices is 1 atmosphere. But as the words that I'm speaking, travel through the air, the local pressure is either slightly less or slightly more than 1 atmosphere, and the regularness of that oscillation between slightly higher and slightly lower pressure is what your ear interprets as sound. All right. With that said, the apparent speed with which a wave appears to move, and which is actually the speed with which the energy in the wave is being transferred, so that speed is equal to the product of the wavelength and the frequency. Or, equivalently, we could say it's the angular frequency divided by the wave number. Now, the speed of waves in a medium is actually fixed. So, like, all waves in water have the same speed, right? It's the speed of sound in water. All waves in air have the same speed, right? The speed of sound in air. It's 343 meters per second. In fact, if there are engineers who spend their entire careers just measuring the speed of sound in various materials. So gases usually have the lowest speed of sound, and then liquids are faster than that. So the speed of sound in water is something like 2,000 meters a second. And then the speed of sound in, say, aluminum is almost 6,000 meters a second. So the denser a material is, the faster waves tend to move through it.
I have a slightly unrelated question. What would happen if you broke the speed of sound, like, underwater?
You can definitely do that. So the same thing that would happen if you broke it in air would happen, right? Like, you'd have a sonic boom. What happens in... Actually, you know what? Are you all familiar with the mantis shrimp?
Yeah.
Okay. So I've got a room full of biology majors here, so I thought it was a pretty good... So the mantis shrimp is one of the most ridiculously badass creatures in the ocean. The speed, so it actually, so there's a genus of mantis shrimps. First of all, they all look like clowns. They all look absolutely ridiculous. But there's a genus of them that actually hunts their prey by punching it. And the speed with which a mantis shrimp can punch out its claw is faster than the speed of sound in water. So what that means is that the water actually cannot get out of the way fast enough. So you get a shock wave in water, and behind the punch you get something called cavitation. So that's areas where there actually is no water. There's a temporary vacuum bubble in the water due to how fast the mantis shrimp punched. When those bubbles collapse, they collapse with enough energy to actually give off light. And it's that shock wave that actually kills a mantis shrimp's prey. So that's what happens if you break the sound barrier underwater.
Gotcha, thank you.
Correctly, that's also kind of how torpedoes work too, and why they're so dangerous to ships.
Yes. So, yeah, I was actually thinking about that too. So even if you have a miss underwater, you have an explosion and actually explosions underwater are way deadlier than explosions in air, because the pressure wave coming off an explosion will crush you in a way that the pressure wave in air just doesn't have the energy to do.
gases compact a lot easier than liquids do.
That's exactly right.
I think there was a question in the chat, just making sure with wave speed that the two equations that were given apply to both longitudinal and transverse waves.
Yes, that is correct. So whether it's a longitudinal or a transverse, the speed is the product of frequency and wavelength.
And just making sure the W there is an omega, right, for angular velocity?
Yeah, angular frequency. In this, but
oh,
yeah.
Okay.
Yeah. And then the K is the wave number. So, knowing that the wave speed in a medium is a constant actually lets us do some interesting things. Let's see. We've been going for almost just over an hour here, so I'm going to do one problem from here, and then we're going to break for 10 minutes. How does that sound to everybody?
I'm good with that.
Okay. All right. So here's the idea. The speed of sound in air is 343 meters a second. The A above middle C on a piano has a frequency of 440 hertz. Oh, you beat me to it, Liz. What I would like, so let's say we have a stage. And there is a speaker on each edge of the stage, which is playing 440 hertz with the same intensity. What I want to sit 10 meters away from the stage, and I want to sit on the left-hand side. And what I want is to not be able to hear that sound. I want destructive interference from the two speakers. All right. So we're going to have speaker 1. Its sound is going to take a path like this to get to us. And speaker 2 is going to take a path like this to get to us. Let's call these lengths L1 and L2. All right, so initially, like these speakers are playing in sync with each other. So they're if you sat right next to them, like you'd hear exactly the same note from one as the other, and it would be in phase. So the way to not be able to hear it is actually, so if you are, like here's a schematic of the wave from the speaker on the left trying to reach you. And here's a schematic. I'm trying to draw at the same wavelength. Speaker on the right has to go a little further to reach you. So you want a trough from one of these. At the same time, you have a peak from the other one. So what we notice is that if we're in terms of cycles, a peak and a trough are half a cycle apart from one another. So we want a half cycle difference. Or 3 halves. Or 5 halves. Right, or 7 halves or 9 halves. Basically an odd number of half cycles difference. That's what gives us destructive interference. And we say odd because the other ones, right, because 0, 2 halves, 4 halves, that just means they're going to be in phase. We'll be matching peak to peak this way if there's a whole number of cycles difference. Right? This gives us constructive interference. What that means is that the difference in the length between speaker 1 and speaker 2 has got to be half a wavelength difference, or 3 halves, or 5 halves, etc., etc. But it's got to be an odd number of wavelengths different between the distances to the two speakers in order to give us a half cycle difference, so that they will cancel out at our seat. Let's say the entire stage is 15 meters wide. And I'm going to drop down some verticals on these. And you know that we're going to break out the Pythagorean theorem at some point. Which, is there anybody who doesn't list the Pythagorean theorem as their top 5 formulas of all time? I assume you all must have some affection for it if you're here in Gen Physics 2.
Sure, why not?
My daughter had to teach summer school math this year because they forced her, and she volunteered to summer school, found out the day before she was going to teach math, and I said, just teach them the Pythagorean theorem. That's it. So teach them ratios and the Pythagorean theorem. So she spent 3 weeks. That was all she did.
That's
she
fantastic.
Would go to the row. What's the Pythagorean theorem? I don't know. A squared plus B squared equals C squared. Next kid, what's Pythagorean theorem? She did it for a week.
Well, they were ready for college then.
I'm telling you, those kids are going to come back and thank you.
Yeah. I lost track of what I was saying. Right.
Sorry, that was me.
Sorry. So the kind of let's actually X direction, Y direction. There we go. So while we're here, I want to extol the virtues of a unified method of problem solving. Right? And this will work for almost all problems you will do for the whole semester, and hopefully your Gen Physics 1 teacher taught you something like this as well. But for every problem, draw a picture. Future you will thank you for drawing a picture to start. Make sure you know what your coordinate system is like. It usually doesn't matter what you choose for your coordinates, but you do have to pick one and then stick with it. If there are vectors to be broken down, break them down. Then reach into your toolbox and see what physics seems to apply. And lastly, clean it up. Do the math. Liz has heard me say this before. But yeah, this is what you want to drill into your minds. So I've drawn a picture.
I'm down. Then you drill this in. That's
Okay. So we've drawn a picture, specified some coordinates. We're sort of breaking down the vectors of like L1 and L2 are vectors here. We want to break it down into their y parts and their x parts. So both of them are going to have 10 as an x part because we want to sit 10 meters from the stage. But we want to think about what their x parts are going to be. So for L2, so this distance off center that we're sitting, that's going to be our x, right? We want to sit x meters off center. So for L2, the distance from the x distance from the speaker to our seat is going to be 7.5 plus x. Right? 7.5 because the whole stage is 15 meters wide. Whereas the horizontal distance from the left speaker to our seat will be 7.5 minus x. Right. So far, so good? Well, then we can write down that the length of L1 is the square root of 10 squared plus 7.5 minus x squared. And L2 is going to be 10 squared plus 7.5 plus x squared. And remember, the thing that we would like is for it to have destructive interference, so we would like L2 minus L1 to equal half a wavelength. So, that actually raises a really good question. What is the wavelength of this wave? We know the frequency is 440 hertz. We know that the wave speed is 343 meters a second. So what's the wavelength? Well, we know from the last page that the product of frequency and wavelength will give us the wave speed. So if we know the wave speed, because, say, we know what the speed of sound in air is, we can do a little rearranging and get ourselves the wavelengths. Uh, 7.5 is half of 15.
15 divided by 2 is 7.
All right, and now we've got, so we'll have square root of 100 plus, and then under here we'll have what? 7.5 squared minus 15x plus x squared minus 100 plus 7.5 squared plus 15x plus x squared equals 0.39. Adrian, that's right. So we're making the assumption that the line I drew, the vertical line I drew, is actually in the middle. It's certainly not the only way we could have set this up. We could have instead, it would have been perfectly fine to say that this distance was x and this distance was 15 minus x. That would also have been fine.
I think I might have just blanked on the part where you were writing in the middle L2 to L1, the wavelength over 2 equals 0.39. I think I just blanked on what we were writing there.
Oh yeah, so we want the difference in the length, the path length from the two speakers to be half a wavelength of the sound we're hearing, because if that's true, then we'll have destructive interference, and the sounds will cancel out.
Okay, thank you. That makes sense.
Okay.
So instead of using wavelength over 2, you can do like 3 over 2 wavelength or 5 over 2 wavelength. Wouldn't make a difference, right?
Yeah, you'll get destructive interference at all those points. Okay. You just want the one that has the shortest.
Which is the easiest. Okay.
Yeah, the one that's closest to the sitting in the middle. Okay. We are past the physics part of this problem. What is left is a messy but doable bit of algebra. So I think we will stop there, and we will have ourselves a little 10-minute stretch. So it's 12:55 by my clock, so I will see you back here at 1:05. And we will talk about hearing. Hanson, no, this is way harder than what I would put on your quiz.
Would a question like this be on the final?
No.
I have a question about this. You're saying that we're now past the physics of the problem. So on a quiz or on a test, are you expecting us to then solve for x, or do you want us to just write it out like you have just written it out?
So if you stopped here, you would get 4 out of 6 points.
Okay.
Full points you'd have to finish it off and solve for x.
Okay, perfect. Thank you.
So I know you said this isn't going to be on a test or a quiz, but will this question be in my nightmares?
Absolutely.
Great.
Can you just clarify where you got the 10 squared?
Pythagorean theorem. So
okay, gotcha. Yeah, I see.
And it doesn't ever work, right? Because your ears are too far apart.
That's actually true.